Welcome back to our AI Teaching Machine Learning System Design series. The problem is to design a system that predicts the LTV of users in a mobile app. Here are some good questions to ask in the requirement clarification phase. What is the definition of LTV for our app? What is the primary goal of the prediction? What types of user data are available? Should the system output point estimates, ranges, or probabilistic distributions of LTV? Are historical transaction logs complete and reliable? In this slide, we frame the LTV prediction task as a supervised machine learning problem. The system takes as input a rich set of user features, including demographics, behavior logs, transaction history, and temporal context. The output is a predicted lifetime value over a specified time horizon, which can be represented as a point estimate, interval, or probabilistic distribution depending on business requirements. Several machine learning models can be used. Tree-based models like XGBoost and LightGBM are highly effective for tabular data, offering strong performance and interpretability. Neural networks, including feed-forward architectures and sequence models like RNNs or transformers, are useful if we want to capture sequential user behavior over time. Survival analysis models help handle censored users who haven't yet churned. The objective is to minimize prediction error using metrics like MAE or RMSE, though we can also incorporate business-aware loss functions that prioritize accuracy for high-value users. Key challenges include handling sparse data, capturing temporal dynamics, managing outliers, and monitoring feature drift over time. This slide set the stage for the subsequent discussion on model architecture, training, evaluation, and deployment. Preparing high-quality data is critical for accurate LTV prediction. We start by collecting data from multiple sources, including user demographics, in-app activity, transaction history, and marketing engagement. Cleaning the data involves removing duplicates, handling missing values, and correcting inconsistencies in formats. Feature engineering is a key step. We create aggregated behavioral features such as average session length, RFM metrics, and cohort-based variables. Temporal features like rolling averages and trends help the model capture dynamics over time. Interaction features that combine demographics with behavior often improve predictive power. Data normalization and encoding ensure that numeric and categorical features are in the right format for the model. Labels are computed based on user spend over the chosen horizon, with special handling for users who are still active to avoid bias. Finally, careful splitting of the dataset into training, validation, and test sets is essential, particularly using time-based splits to prevent leakage in temporal predictions. Rolling window validation or cross-validation techniques can further improve model reliability. Predicting user lifetime value involves capturing complex patterns in historical user behavior and transactional data. Tree-based models like XGBoost, LightGBM, and CatBoost are highly effective for tabular data with heterogeneous features. They can capture nonlinear relationships, interactions among variables, and are robust to missing values. Random forests offer a simpler, more robust alternative for smaller datasets. One key advantage of tree-based models is interpretability. They provide feature importance scores that help product managers understand which behaviors drive LTV. However, tree models struggle to capture sequential or temporal dependencies inherently. This is where neural networks excel. Feed-forward networks, MLPs, can combine engineered features such as recency, frequency, monetary, RFM metrics, engagement metrics, and derived features like rolling averages or time-based trends. They are flexible and capable of modeling smooth, continuous relationships, but require careful pre-processing, normalization, and regularization to prevent overfitting. Recurrent neural networks, RNNs, including LSTM and GRU, explicitly model sequences of user events, sessions, and transactions. They maintain a memory of past behavior to predict future value contributions. LSTMs excel at long-term dependencies, while GRUs are lighter and faster, but slightly less expressive. Attention mechanisms can be incorporated to allow the model to focus on particularly important events, such as large transactions or highly engaging sessions. Transformer-based architectures take this a step further. Using self-attention, transformers capture long-range dependencies more effectively than RNNs, enabling the model to weigh relationships across distant events in the sequence. They also handle multimodal input elegantly, allowing integration of textual events, categorical embeddings, and numerical features. Positional encodings preserve temporal order, ensuring the model correctly interprets sequence timing. Transformers are highly parallelizable, which accelerates training on large datasets. Hybrid approaches combine the strengths of both paradigms. For instance, embeddings from a transformer encoding user behavior can be fed into a gradient-boosted tree model. This approach leverages sequential modeling from the neural network while retaining the strong tabular prediction power and interpretability of tree-based models. Feature engineering remains critical. Core features include RFM metrics, engagement patterns, session length, clicks, retention, and derived temporal features, rolling counts, averages. Categorical embeddings for user segments, geography, and device types add additional signal. When selecting a model, consider several factors: dataset size, the importance of temporal dependencies, inference speed requirements, and production constraints. Tree-based models are generally faster and easier to serve at scale. Neural networks, particularly transformers, offer potentially higher predictive accuracy for sequence-heavy datasets, but require more computational resources, especially during training and inference. Finally, the choice may also be influenced by interpretability requirements. Tree-based models are inherently more interpretable than deep neural networks, though techniques like SHAP or attention visualization can help explain neural network outputs. Neural networks allow us to model complex patterns in user behavior that tree-based models may miss. Starting with simple multi-layer perceptrons, MLPs, these feed-forward networks accept tabular features such as RFM metrics, recency, frequency, monetary value, engagement statistics, session duration, app opens, and categorical embeddings, user type, geography, device. MLPs learn nonlinear relationships between these features and predicted LTV. They are flexible but cannot inherently capture sequential behavior. To model sequences of user activity, we turn to recurrent neural networks, RNNs. RNNs process data in a time-ordered fashion, maintaining a hidden state that summarizes past events. LSTM, long short-term memory networks, enhance standard RNNs by introducing gated mechanisms, input, forget, and output gates that regulate how much past information is retained or forgotten. This allows LSTMs to capture long-term dependencies in user behavior, such as recurring subscription patterns or multi-week engagement trends. GRUS, gated recurrent units, are a lighter alternative to LSTMs. They combine input and forget gates into a single update gate, reducing computational cost while maintaining good performance on shorter sequences. Transformers offer a more powerful approach for sequential modeling. Using self-attention, they compute relationships between all events in a sequence simultaneously rather than sequentially like RNNs. This allows transformers to capture long-range dependencies efficiently. In LTV prediction, a transformer can weigh highly influential events, like a big purchase or a promotional response, more heavily than routine actions. Transformers also handle multimodal input, integrating textual data, for example, customer reviews, categorical features, and numerical metrics. Positional encodings ensure that the model retains information about the temporal order of events, which is critical in predicting future value contributions. Hybrid architectures combine sequential embeddings from RNNs or transformers with MLP layers or tree-based models. For example, the output embeddings from a transformer can be fed into a gradient-boosted tree to leverage both sequential understanding and strong tabular learning. This often improves performance, especially when sequences are long but tabular features remain important. Training considerations: RNNs can suffer from vanishing gradients on very long sequences, while transformers require more memory but can be parallelized efficiently. Regularization techniques, dropout, and careful embedding initialization are important to stabilize training. During inference, transformers may offer faster predictions due to parallelization, while RNNs process sequentially, potentially increasing latency. Evaluating an LTV prediction model requires a combination of offline metrics, online metrics, and ongoing monitoring in production. Offline metrics: standard regression metrics like mean squared error (MSE), root mean squared error (RMSE), and mean absolute error (MAE) quantify how closely the predicted LTV matches the actual user value in historical data. R-squared provides insight into how well the model explains variance in user value. If the model predicts LTV distributions rather than point estimates, quantile loss can measure how well the predicted percentiles match reality. Calibration plots are also critical. They compare predicted LTV ranges with actual observed values to check for systematic under or overestimation. Online metrics/A/B testing. Offline metrics cannot capture all business realities, so running controlled experiments in live settings is essential. For example, using model predictions to guide marketing or retention strategies, we can measure the actual revenue lift or improvements in retention for targeted user segments. Engagement metrics like conversion rate, churn reduction, and purchase frequency provide additional evidence of model efficacy. Business KPIs alignment. Beyond statistical metrics, the model must support strategic goals. This includes evaluating the ROI from marketing campaigns, using predicted LTV to prioritize users, ensuring that high-value users are correctly identified, and measuring cost-effectiveness of interventions. Serving/monitoring. Deploying LTV models requires attention to latency and throughput, particularly for real-time scoring of users. Monitoring for drift in feature distributions or in LTV prediction performance is necessary, as changes in user behavior may degrade the model. Retraining triggers should be established based on monitored performance decay, ensuring the model remains accurate over time. By combining offline evaluation, online testing, KPI alignment, and robust monitoring, the organization can maintain trust in LTV predictions and leverage them effectively in business decisions. Serving an LTV prediction model involves deploying it in a way that both business operations and ML monitoring requirements are met. Serving modes. There are two primary ways to serve the model. Real-time scoring is essential when predictions are required on demand, for example, during a live marketing interaction. Batch scoring is useful when predictions can be pre-computed, such as updating user segments nightly. Infrastructure and deployment. Real-time inference requires APIs that can handle variable traffic while maintaining low latency. Batch scoring pipelines run periodically, generating updated LTV predictions for large groups of users. Both approaches benefit from scalable cloud resources or on-premises solutions depending on organizational requirements. Monitoring and logging. Continuous monitoring ensures model reliability. Latency and throughput metrics track system performance. Prediction distributions should be monitored to detect drift in feature patterns or in the LTV predictions themselves. Detailed logs, including input features, predicted LTV, and eventually actual outcomes, enable auditing and model performance assessment. Model retraining and updates. Performance degradation is inevitable as user behavior changes over time. Automated retraining pipelines and careful version control allow new models to replace outdated ones seamlessly. A/B testing and canary deployments help assess impact and reduce risk before full-scale rollout. Security and compliance. User data is sensitive, so GDPR compliance, secure storage, and strict access control are mandatory. Ensuring that data privacy policies are enforced during both serving and retraining is critical for regulatory and business trust. By combining efficient serving, rigorous monitoring, controlled updates, and strong security practices, LTV prediction models can be reliably operationalized to support real time decision making and strategic initiatives.